Hello, welcome to the section of Math 19661 about complex numbers. In this first video, I'm going to introduce complex numbers. So, in order to introduce complex numbers, let's think back to the first types of numbers we learned about when we started learning mathematics. The first types of numbers you learned about were probably the numbers you use for counting. So, positive whole numbers, 1, 2, 3, 4, and so on. And you then learn some operations with these numbers. Positive whole numbers, you can add them together. And then you want an inverse operation for adding them together. That's subtracting whole numbers, which is the inverse of adding them. But there's a problem that comes along with subtraction when you only have positive whole numbers, and that is that you can subtract some of them and that you no longer have a positive whole number. So for example, if you take 1 minus 5, that would be negative 4. It's not a positive whole number, so you have to introduce negative numbers in order to make subtraction complete. All right? In order to be able to subtract any two numbers, you have to introduce the negative numbers. Right? And so then you also learn about multiplication of positive whole numbers. So you have two sets of 3 objects. That's multiplying 2 times 3, you get then 6 objects total. This is a natural operation that you learn about. And then you want to be able to go the other way, do the inverse operation of multiplication, which is division. But now you have another problem, which is that if you try to divide two whole numbers together, then that may not be a whole number anymore. Of course, if you divide, say, 1 by 4, that is then a fraction, or a decimal, 0.25 or 1/4. And so in order to make division a complete operation, you have to introduce rational numbers. So those are fractions of whole numbers. Right? And then after this, you learn about decimal expansions of numbers. So like I said, 1 divided by 4 is 0.25. And so we learn about what that means, 0.25, and then you can realize that any rational number, the ratio of two whole numbers, has a repeating decimal expansion, or possibly the decimal expansion terminates at a finite number of decimal places, which means that there could be other numbers who have decimal expansions that don't have a repeating pattern or don't terminate at a finite number of places. And those are irrational numbers. And so in order to make these sorts of decimal expansions complete, you have to introduce the rational numbers, and then you take rational numbers and irrational numbers together. Those are the real numbers. Right. So we then have the real numbers, and we want to now, in order to introduce the complex numbers, extend the inverse operation of squaring a number. So we know how to multiply a number by itself when it's a real number. And a number multiplied by itself, and a real number multiplied by itself, is going to be a positive number. And the inverse of that is taking the square root. When you take the square root of a positive number, you get another positive number whose square is that original number. So we want to be able to extend this operation to all the numbers. And how can we do that? Well, this is where we introduce complex numbers. And so when we introduce complex numbers, we introduce a new quantity whose square is -1. This is a square root of -1. And we normally denote this new quantity by I, the notation which is shown here. In some disciplines, it's also denoted by J. I think mostly in electrical engineering. In this class, I'm going to be denoting it by I. And this is called the imaginary unit, and it's defined by this property that when you take I squared, you get -1. It's a square root of -1. Right? And as I said, this quantity is called the imaginary unit. So imaginary numbers are real numbers times this imaginary unit. So we can do arithmetic with these imaginary numbers. So for example, if we have 2 times I plus 3 times I, we simply add the coefficients of I together, treating I kind of like it was a variable in a polynomial equation. So 2 plus 3 is 5, 2I plus 3I is 5I. And you can do the same thing with multiplication. So 2I times 3I is going to be the product of the coefficients, 2 times 3, which is 6, times I, so I squared. And as we've defined I here, I squared is -1, so 6I squared is -6. So 2I times 3I is -6. Okay, so I is a square root of -1. And so we can take square roots of other negative numbers. So the square root of -9, for example, could be either plus or minus. When we take a square root, remember there's two square roots, really, the positive one and the negative one when we have real numbers. And so we take a square root, there's either plus or minus the square root of 9, and that's the real number, square root of 9, times I, the square root of -1. So this is plus or minus 3 times I, because 3 is the square root of 9. Okay, so that's imaginary numbers. Now complex numbers are numbers that are formed by adding a real number plus an imaginary number. So for example, we have 2, real number, plus I, imaginary number. 2 plus I, that's a complex number. 3 minus 4i, another example. Square root of 2, that's an irrational number, plus pi, another irrational number, times I is another complex number. So in general, a complex number is a real number, written here as a, plus another real number times I. A plus b times I. So a and b are both real numbers. So sometimes people ask about whether b times I is the same as I times b. So we have this commuting property. So a plus bi just means the same thing as a plus ib. The imaginary unit commutes with the real numbers when you multiply them together. Do it in either order. The order there doesn't matter. All right, and so there's some terminology associated with these complex numbers. So first of all, a is the real part of the complex number z. So z is a plus ib. This is written as real part of z, re of z. B is the imaginary part of z, just written as im for imaginary z. And it's important to note here that b is itself a real number. The imaginary part of a complex number is a real number. The real number you multiply times I, the imaginary unit. So just as an example, if z is 2 minus 3i, the real part of z is 2. The imaginary part of z is -3, which is the coefficient of I in this expansion. All right, so once again, note, the imaginary part is actually a real number. This is something that sometimes confuses people when you first see it. You think the imaginary part should be an imaginary number, but it's actually a real number. Okay, so let's talk about how we can do arithmetic with complex numbers. So we can do the same operations that you can do with real numbers I was discussing at the beginning: addition, subtraction, multiplication, division, with complex numbers. So first of all, addition, there's not really any problem here. So we have two complex numbers. In order to take the sum of these two complex numbers, we simply add the real parts together and add the imaginary parts together. So we have 1 plus 2i plus 3 minus I. The sum of the real parts is 4. The sum of the imaginary parts is 2 minus 1, so 1. So the sum of these two complex numbers would be 4 plus I. Okay, what about multiplication? This gets a little bit more complicated, but the idea is still you simply multiply out the two complex numbers using the distributive law, as you understand it, treating I like it was a variable in a polynomial equation, and then you just replace I squared by -I wherever you see it. So let's do this for this example. Suppose we want to compute 1 plus I times 3 minus I. So first of all, we multiply this out using the distributive law. So we have 1 times 3 is 3. And then we would have 3 times 1 minus 1 times I. So that's 2i. And then we would have I times -I, -I squared. So when we use the distributive law to multiply this out, this is what we would get. Right, and then we replace I squared where it appears here by -1. So the I squared here is -1, -1 is 1, so we get 4 plus 2i. Right, as another example, just to stress this, suppose we want to multiply together 1 plus I and 2 plus 3i. So first we multiply it out using the distributive law. 1 times 2 is 2, and we have 2 times I plus 3 times I, which is 5i. And then we have I times 3i, so that's 3i squared. And then we would replace this I squared by -1 and would get -1 plus 5i as the final final product of these two complex numbers. So you have 2 plus 3 times -1. This -1 takes the place of the I squared. Right, so this is the multiplication of complex numbers. All right, there are some other operations. We're going to talk about division in a moment. Subtraction is just the opposite of addition, which is easy to see. You simply subtract the real and imaginary parts, just like the addition. Division is a bit different, and we're going to discuss that in a minute. But first, we're going to talk about some other operations for complex numbers that don't have an analog for real numbers. So one of them is the complex conjugate. So for a complex number, z equals a plus b times I, its complex conjugate is what you get when you simply put a negative sign in front of the imaginary part. So multiply the imaginary part by -1. And we write the complex conjugate using this line here over the imaginary number. We say z bar for the complex conjugate is a minus b times I. All right, so just two very simple examples. If z is 2 plus 3i, then z bar, the complex conjugate, is 2 minus 3i. If z is 2 minus 3i, z bar is 2 plus 3i. So it goes back and forth, of course, because you just multiply the imaginary part by -1. The complex conjugate of the complex conjugate is the same number again. Okay, so an important example occurs when we multiply a complex number by its complex conjugate. So here we have z, complex number, a plus bi, times z bar, which is the complex conjugate of z. So this is a plus bi times a minus bi. So we work this out just like described on the previous slide. First, use the distributive rule in order to multiply out z times z bar. So we have a times a squared, plus abi minus abi. So the plus comes from the product of these two terms, and the minus comes from the product of the outer terms. And then we have plus bi times negative bi, so minus bi squared. Okay, and so the two terms that have a I in them here cancel out. This I squared becomes -1, and so we get a squared plus b squared, which is a real number and a positive one. In fact, this is something we call the modulus of z squared, and we're going to discuss that more in the next video. But this z times z bar gives us the real part squared plus the imaginary part squared. Okay, and so I guess I just haven't written what I was saying. So we're going to discuss this modulus of z more in the next video. It's akin to the modulus of a real number, or the absolute value of a real number. Okay, so now we're ready to talk about division of complex numbers. Suppose we have 1 plus I divided by 2 minus I. We want to show that that is a complex number, or write that as a complex number. So identify what is the real part of 1 plus I and the imaginary part of this complex number. So what is the real part of 1 plus I divided by 2 minus I and the imaginary part of that number? So write it in this form a plus bi. Now how can we do that? Well, in order to do this in general, we use the fact that z times z bar is a real number. So we have two complex numbers, w and z, divided, and we multiply by the denominator complex conjugate divided by the denominator complex conjugate. And then in the denominator, we get z times z bar, which is a real number, the modulus of z squared. And so once we've done that, we can identify the real and imaginary parts. So let's do this example that is stated at the beginning of the slide. Switch over to the visualizer for this. So we have 1 plus I divided by 2 minus I. All right, and as it's shown there, we're going to multiply and divide by the complex conjugate of the denominator. Then we're going to have 1 plus I times the complex conjugate of the denominator, 2 plus I. The complex conjugate is obtained just by multiplying the imaginary part by -1, divided by 2 minus I times 2 plus I. right? And so once we work this out, the numerator and the denominator, we'll see what the real and imaginary parts are of this quotient of two complex numbers. And so in the numerator, let's multiply this out as we've done for the other multiplication. So we have 1 times 2 is 2, plus 2i plus I, so plus 3i, and then plus I squared. Now in the denominator, we have this complex number, 2 minus I times its complex conjugate. We know that's going to be the real part squared plus the imaginary part squared, but let's multiply it out just to see that anyway. So 2 times 2 is 4, and we have minus 2i plus 2i, which will cancel out. Let me write it in just to make it more explicit. We have the minus 2i plus 2i, and then we have minus I squared. Okay, and so now we just need to replace I squared by -1, both in the numerator and the denominator. And so this I squared is -1. Combined with the 1, we get 1 plus 3i. And then in the denominator, these two cancel out. We have 4 minus -1, so that's 4 plus 1, 5. All right, and so this complex number is 1/5 plus 3/5 times I. The real part is 1/5, the imaginary part is 3/5. Okay, so this is this example of a quotient. We use the complex conjugate of the denominator in order to determine the real and imaginary parts of the quotient of two complex numbers. Show that the quotient of two complex numbers is again a complex number. All right, so we introduced complex numbers by adding square roots for negative numbers. And so, in fact, introducing complex numbers allows us to write solutions for any quadratic equation. Before, when we didn't have complex numbers, some quadratic equations had no solutions. They have no real number solutions. But when we use complex numbers, quadratic equations, such as this one, ax squared plus bx plus c equals 0, always have solutions. And we just have this b squared minus 4ac, which could be negative. And then when that is negative, we get a complex number solution. So yes, if b squared minus 4ac is less than 0, when we only deal with real numbers, there's no solutions. There's no real number solution. But now, there could be real number solutions. We have a square root of a negative number. And so we have these solutions for quadratic equations even when b squared minus 4ac is -1. So let's look at an example of that. So we have this quadratic formula, x squared minus 2x plus 5 equals 0. And we can simply write down the solution by using the quadratic formula, which is shown there on the slide. But you may wonder, how do we know that the quadratic formula holds when we use complex numbers? Well, the reason we know the quadratic formula holds is we can complete the square. So let's just go through that in this example. So we do what's called completing the square. And what that means is we just write this x squared minus 1 as a square of some expression involving x. So this x squared minus 1 is going to be x minus 1 squared minus 1. So note that this gives us x squared minus 2x, and then plus 1. We have to subtract off the 1 because we have a plus 1 there. And then plus 5 equals 0. All right, so this would be x minus 1 squared equals -4. Now let's take the square root of both sides and get x minus 1 equals plus or minus the square root of -4. And of course, when we just had real numbers, we would have to stop here. There's no square root of -4. That's a real number. But with complex numbers, this is plus or minus 2i. Right? Plus or minus 2i squared is -4. And so then we can solve for x. So x equals 1 plus or minus 2i. All right. Just to check that we get the same thing from this process, completing the square, as the quadratic formula. Let's use the quadratic formula as well. I'll write down the solution. Now suppose we use the quadratic formula, which is what's shown there on the slide. And we have x equals negative b. b here is -2, so negative b is 2, plus or minus the square root of b squared, that's 4, minus 4a times c. A is 1 and c is 5, so minus 20 divided by 2a, and a is 1, so just divided by 2. All right, and so then we can cancel the 2's, 1 plus or minus the square root of -16 divided by 2. And the square root of -16, well, we wouldn't have a square root of -16 if we only used real numbers. But with complex numbers, the square root of -16 is 4 times I divided by 2. And 4 divided by 2 is 2. So 1 plus or minus 2i. The same result we got from completing the square. Okay, so usually it's easier just to use the quadratic formula, but the quadratic formula comes from completing the square, which also works for complex numbers. All right. So let's look at one other example. Finding all the solutions of a higher order polynomial equation. So this is a fourth order equation, x to the fourth minus 1 equals 0. In fact, when we go to complex numbers, as it turns out, there will always be solutions of polynomial equations, and there will be the same number of solutions as the degree of the equations when you count the solutions with multiplicity. So the multiplicity is the number of times a root occurs in a factorization of the polynomial. And so we say that complex numbers are complete in this sense, that you always have the same number of solutions of a polynomial equation as the degree of the polynomial. All right, and so let's show what are the complex number solutions of this equation, x to the fourth minus 1 equals 0. All right, so the equation is x to the fourth minus 1 equals 0. And so in order to solve polynomial equations, you want to factor the polynomial. And so this is a difference of squares. X to the fourth is x squared squared, and 1 is 1 squared. So this is x squared minus 1 times x squared plus 1 equals 0. And so if we were only dealing with real numbers, this would always be positive. X squared plus 1. X squared for real number is always a positive number. So this would never be 0. So the only two solutions would be the solutions where the first factor here is equal 0, which are just going to be plus and minus 1. Right, so this x squared minus 1, it says x squared equals 1. X equals either plus or minus 1. But when we have complex numbers, if x squared plus 1, that would be 0 if x squared equals -1. And so that would be 0 if x equals plus or minus I, the two square roots of -1. I is a square root of -1, and then negative I, also a square root of -1. All right, so there are 4 different solutions for this fourth order polynomial. X is equal to plus or minus 1 and plus or minus I, or plus or minus I. Okay, so that's the end of the first video. In the next video, we're going to discuss how we can visualize complex numbers. For real numbers, we have the real number line. We visualize them, negative numbers on the left, positive numbers on the right. For complex numbers, we have a different way of visualizing them in a plane, and this is going to be the topic of the next video.